Let's talk about API security today. When you have a public API endpoint, that endpoint most definitely needs to be protected. What are the most important things for securing REST APIs? Transport layer security. Use HTTPS and the most current cipher suits and the most current version of TLS. Do access control. If you use tokens, JWT is the new standard. And you should always validate those JWT tokens, preferably with a signature. So API keys are not security. Don't consider an API endpoint with only API key validation to be secure. Restrict the HTTP methods that are allowed. Do some input validation. Validate also the content type. Then hide your management endpoint. Do correct error handling. Audit logs need to be protected. Do some sanitization of the stuff that you put into the audit log. All security relevant stuff should go in the audit log because there you can do pattern detection on some type of attacks. CORS headers, include them if you want to support CORS, and be as specific as possible. Then sensitive information HTTP requests, use the right place for sensitive information, use the right HTTP return code or status code. That's it. These are best practices for REST APIs. One of the prerequisites for doing any kind of protection of the actual endpoint is that you need to protect all the data flowing in and all the data flowing out. So HTTPS, transport layer security with the latest type, is absolutely required if you want to have a secure API. Yeah, HTTPS. Without HTTPS, you can't have secure APIs. It protects your authentication credentials, right? Authentication credentials come with every API request. There is nothing like a server-based session. So in every API request, you have some kind of credentials. You have either basic auth, not really recommended, but could be there, or you have auth access tokens. Those come with every request, need to be protected. You have an API key, comes with every request, needs to be protected. So HTTPS also allows clients to authenticate the service. All right, so the client knows, yes, that's the server because of the certificate. So the certificate gives the client some kind of guarantee for the integrity of the data. What you can also do, not for public APIs, but for partner APIs, you could think about having mutually authenticated client-server certificates. And that is something that's used in a business-to-business case most definitely all the time. Good. So that was it for protecting what actually goes over the wire. Next point to protect is, well, access control. Non-public REST services must perform access control at each API endpoint. Each API endpoint, right? It's not like you go once, you log in, and then you have your session like you sometimes used to do. It's with every request that you need to do the access control. Web services and monolithic applications implement this by means of user authentication, authorization logic, and session management. This has several drawbacks. For modern architectures which compose multiple microservices following the RESTful style. In order to minimize latency and reduce coupling between services, the access control decision should be taken locally by REST endpoints. And user authentication should be centralized in an identity provider which issues access tokens, right? So those two things, think about this for access controls. And you're going to be good. Next point is, how are those access tokens, or those tokens in general that we talk about, how are they structured? And it seems like there is some convergence towards JSON Web Tokens, JWT. And that's the format for security tokens. JWTs are basically JSON data structures that contain a couple of claims which are standardized and that then can be used for access control decisions. They have a cryptographic signature or a message authentication code that protects the integrity of this JWT token, JWT JWT. Ensure that the JWT are integrity protected, right? Because you can do the cheap JWT token, and there you just select as an algorithm, as your signature algorithm, none, right? That's not really a JWT. It's not integrity protected. So as a best practice, if you get a JWT and there is an algorithm none, don't accept it. And if you're the provider, don't ever give that out to anyone except maybe for debugging purposes. So in general, signatures should always be preferred to MACs for integrity protection, right? So don't use message authentication codes if you have the chance to give out signatures. Why? Because if you use a MAC for integrity protection, then the service that can validate the JWT token with the message authentication code can also create new JWT tokens using the same key. And that means that all the services using the same key have to mutually trust each other. And another consequence of this is that there's a compromise of any service also compromises all the other services that share the same key, right? So that's why you need to be careful with message authentication codes. So you verify the JWT before you use the claims, because the claims are easily accessible. You can decode them, you can use them, but before using them, you need to validate the token. And the client, well, in this context of identity is usually called a relying party. So the relying party must verify the integrity of the JWT token based on its own configuration or hard-coded logic. It must not rely on any information in the JWT header to select the validation algorithm. Okay. That's interesting because there is this header, Joe's header, JSON object, signature, and encryption header. And in this header, we have an algorithm, right? It's coded in there. Now we say, don't ever trust that, but always trust what has been published on the website of the identity provider and use that hard-coded. And don't trust that token, the content of the header at least. So in the JWT token, there are some claims that are standardized, and you can go read up, for example, on the JWT specification. For example, there's the ISS for issuer. It's a trusted issuer, right? Is it the expected owner of the signing key? So you need to check the issuer, and don't just trust that it's going to be all right. Check it against the signing key. Audience, AUD is the claim. Is it the relying party? Is the relying party part of the target audience of this JWT? Right? In the audience field, you can actually specify a whole number of audience or a number of clients, but your own client ID needs to be part of the audience. Then we have EXP, expiration time. Is the current time before the end of the validity period of this token? That's an easy one, right? You just check the current time, you check the expiration time. Have we expired? Well, if we have expired, don't trust the token. And then we have something similar, NBF, not before time. Is the current time after the start of the validity of the token's validity. Because you can also give out future tokens. You can say, this is not valid before a certain period of time, right? So you also need to check, you need to kind of check the window where it's okay to have for this token to exist. And there it's expiration on the one side and not before on the other side. Next topic, API keys. Public REST services without access control, they usually have the risk to get lots of traffic. And if you're on some public cloud, that means you get a lot of high bill, because you use a lot of bandwidth, you use a lot of compute. So that should be avoided. What you do is, if it's a public endpoint, right, you don't really want to protect it, but what you at least give out then are API keys. And those API keys can be used to mitigate the risk a little bit. It's not a lot. They are often used by organizations to monetize API instead of blocking high frequency calls. Clients are given access in accordance to purchased access plans, right? So you give specific clients who have purchased, for example, your gold plan. You give them an API key, and when that API key comes, you can identify, that's the client with the gold plan. API keys can reduce the impact of denial of service attacks, right? However, when they are issued for third-party clients, they're relatively easy to compromise. You can't really control what the client does with those API keys. They maybe have them on their GitHub repository. They get farmed. They get there are bots going around on the repository trying to get API keys. If there are too many requests, then you return a 429, too many requests, HTTP status code. You can also revoke the API key if some clients violate the usage agreement or repeatedly violate it. And you should not exclusively rely on API keys for protecting sensitive, critical, high-value resources. Another thing that you should always do to protect your API endpoints is restrict the HTTP methods. And that's something that you usually do on an API gateway when you have one. So you apply a whitelist of permitted HTTP methods. For example, if you have a read-only endpoint, only give it read access, right? Only give it a get access. Or you say it's only a get and a post if you have read-write, or get post put for read-write. So really limit those HTTP methods that you can apply. Then you reject all requests that don't match this whitelisted HTTP methods. And what do you give as a response? You give as a response a 405 method not allowed. Right? That's the status code that you send out. If, for example, you've whitelisted get post put and someone comes with a patch, well, there you go, 405. Make sure the caller is authorized to use the incoming HTTP method on the resource. And this authorization means also that you have identified the user and you, for example, got the access token of that user, because you know the identity of the user, and you also, or you at least know a user has been authenticated. You don't really get the identity, but you know that he has been authenticated sometime in the past, and you have checked the scopes, you've checked the access rights that have been granted by the user himself. So that should be done always. The scopes should be set on the access token to differentiate between different HTTP methods, or at least between read and write. So if you have a resource that's called address, you have two scopes, a read scope and a write scope, read address, write address, and then you differentiate between those two. If someone has only the read address and tries to do a post on the address resource, you just deny it, right? So that's best practice. Restrict HTTP methods and do this via access token scopes. Another thing you should always do is input validation. Do not trust input parameters or objects. Well, this is something we do for a long time already. You need to validate it. You validate the length, you validate the range, the format, and the type. You achieve an implicit input validation by using strong types like numbers, boolean, dates, times, or fixed data ranges and API parameters. That, for example, if you have a object coming in, then you have this object defined by a schema, by a JSON schema, for example, and then you can validate all these types. Then if you require a string input, you need to have a regex that kind of limits whatever can be in that string. Anything that's unexpected or illegal, just reject it, right? Then you need to make use of validation libraries in your API. You sanitize any input that comes in before you start processing it. And there's lots of libraries that you can use. And so really make use of those. Then request size has to be limited, right? You always want to check that request doesn't get over whatever you expect as a reasonable limit. And if the request gets too big, you send a status code 413, request entity too large, right? Simple as that. Sometimes you start with a very low limit. And then as soon as you get some initial pilot traffic, you see how big those requests actually are in real life, and then you adjust your limits. But it's something that you can really easily implement on an API gateway. Then logging of input validation failures. I mean, there is certainly a trade-off. You really should apply also some patterns. If there's a lot of input validation failures from the same client, if you can identify them, probably not good. Probably should revoke access tokens or API keys that client has. You need to use a secure parser, just as you use input validation libraries, sanitation libraries, use a secure parser. Okay, next topic is validation of content type. A REST request and response body should always match the content type header that is set for this specific request or response. Otherwise, you could misinterpret whatever is in the body. Content type header is an HTTP header. So what you should do is you validate the request content type. So if the request content type is either unexpected, or if the input is unexpected and the content type is not known, then you just give a 406 unacceptable or a 415 unsupported media type, right? So if you have a media type that's coming in as a request that you don't support, you give the 415 unsupported media type. If there is some request coming in and that just doesn't match the content type that you have, that you can process in your API, you put out a 406 unacceptable. If you have the XML content type, then you need to have specific parsers that are hardened, because those could be attacked. There are certain attacks that just target a specific XML parser. Sometimes there are API gateways that capture those attacks. If you have one in front of your API endpoint, all the better. If you don't, you need to use a really hardened XML parser. You shouldn't accidentally expose unintended content types. Then you should send safe response content types. It's very common for a REST API to allow multiple response types. For example, you can allow that there is an XML sent out and a JSON sent out, depending on, well, on the request. So the request can kind of specify which of those two supported content types in the response will be used. We should not simply copy the accept header to the content type header of the response. That's a typical anti-pattern that you can see very often, that you just take the same content type and it's not actively managed. Should be very active actively managed by the endpoint. You should reject the request with a 406 not acceptable response if the accept header does not specifically contain one of the allowed types. All right, then the respective HTTP response should be sent. Services including script code, for example JavaScript, in their responses must be especially careful to defend against header injection attacks. Then you have management endpoints, and you should avoid exposing management endpoints via the internet, right? For example, you have an API gateway. The API gateway has a management endpoint, should not be exposed, should just be internally exposed. So if you have the possibility to, for example, have several network devices, either physical devices that go on different networks, one goes to the external zone, one goes to the internal zone, then map the management endpoint only to the internal zone. If management endpoint must be accessible over the internet, then, well, what should you do? You make sure that the user must use strong authentication. For example, two-factor, multi-factor. Expose the management endpoint via a different HTTP port. That's advisable. And restrict access to the endpoint by firewall rules, for example, only to a specified whitelisted IP range or similar things. Next big topic is error handling. You should always, from a security perspective at least, respond with very generic error messages. And you should not reveal any internals in your error messages. Avoid revealing details of the failure that are unnecessary and they're just for debugging purposes of your endpoint, right? Stack traces, for example, they should never be exposed. You should also manage this. For example, if there should be a stack trace that somehow gets through as a response of your endpoint, you need to filter this out at one of the gateways, firewalls that you have before. Then you do not pass technical details, right? Internal hints about stuff, and of course the stack trace that does not work. Audit logs. You need to write audit logs before and after every security relevant event. You should consider logging token validation errors to detect attacks. So just have a history, and then you can do some kind of pattern detection on those error messages in the audit log. You take care of log injection attacks. You need to sanitize all the stuff that goes into the log so that no one can create some script or something that goes into the audit log and then gets executed by, for example, a viewer or somewhere in the audit management system. Good. Security headers. Security headers should be there and you should use them correctly. So you should make sure that the content of a given resource is interpreted correctly by the browser. The server should always send the content type header with the content type, and preferably the content type header should include the character set. The server should also send the X minus content type minus options, and there include the no sniff to make sure that the browser does not try to detect a different content type than what's actually sent. Additionally, the client should send an X-frame options deny to protect against drag and drop clickjacking attacks in older browser. Next topic, CORS, cross-origin resource sharing. CORS in short. That's a standard for having some flexibility regarding cross-domain requests and cross-domain resource sharing. And to filter out when it is allowed and when it should not be allowed. It works like this, that you send a CORS header from your endpoint. It's a specific header or a specific number of headers that you need to set and that signals to the browser what is actually allowed, right? What should the browser accept as an origin? JavaScript calls from origins that are not allowed can be blocked out. A couple of things that you need to consider. You should disable course header in cross-domain calls if they are not supported at all, right? If you don't want to support any cross-domain calls, then disable course at all. And then in the course header, you can put wildcards. That's very nice for debugging purposes, but not for production, right? For production, you should be as specific as possible in your course header what you allow. Then you have sensitive information in HTTP requests. Sometimes the API request, RESTful web service, should be careful to prevent leaking credentials. Passwords, security tokens, and API keys, they should not appear in the URL. They should always be in the header. Because the URL can be captured by web server logs. In post and put requests, sensitive data should be transferred in the request body or in the request header, right? Post and put, because it is very specific to the content type, you can put them in the request and in the body. If you have a get, only put it in the HTTP header. Don't put, for example, a token or an API key in the URL. Then you have HTTP return codes. HTTP defines a number of return codes that need to be used in the right way. When designing a REST API, don't use the 200 response for anything else but for success, right? 200 means success. If there are error codes, then you can differentiate between errors that are made by the clients, then these are the 400 class errors, and you can be more specific which 400 it is. And if the server has a problem, it's a 500 error. And those should be used correctly. Not going into detail of all the different status codes for now, but that's it. That are some of the best practices for securing REST APIs.